Beyond our small blue planet, past the familiar glow of our sun, lies an endless expanse filled with worlds we're only beginning to understand. Out there, orbiting distant stars, exist planets so strange, so extreme, that they challenge everything we thought we knew about how worlds could be. These are the exoplanets, alien worlds circling suns that are not our own. Since the first confirmed discovery in 1992, scientists have identified thousands of them, each one a unique experiment in planetary physics. Some are hot enough to vaporize rock. Others are locked in endless twilight, their faces forever turned toward their stars. A few rain glass sideways through atmospheres torn by winds faster than sound itself. Tonight we'll journey through space to visit some of the most extreme planets ever discovered. These aren't horror stories, but rather windows into the remarkable diversity of the cosmos. Each world, however inhospitable, teaches us something new about the forces that shape planetary systems, including our own. So settle in, relax, and let's explore together the beautiful strangeness of worlds beyond our reach. Before we meet these distant worlds, it's worth understanding how we find them at all. After all, exoplanets don't shine with their own light, and they're impossibly far away, trillions upon trillions of miles from Earth. Most exoplanets are discovered through a technique called the transit method. Imagine watching a distant streetlight and noticing it dims ever so slightly at regular intervals. Something small is passing in front of it, blocking a fraction of the light. This is what telescopes like Kepler and TESS do, watching hundreds of thousands of stars simultaneously, waiting patiently for that telltale dimming that signals a planet crossing in front of its star. The James Webb Space Telescope, our newest eye on the cosmos, takes this further. By analyzing the starlight that filters through a planet's atmosphere during these transits, Webb can identify the chemical fingerprints of gases present there. This is how we know about iron vapor clouds and scorching temperatures on worlds we'll never visit in person. It's detective work on a cosmic scale, piecing together the nature of entire worlds from the faintest whispers of light. Our first destination lies about 64 light-years away in the constellation Vulpecula. HD 18D9733b appears at first glance rather beautiful. Observations suggest it would look deep azure blue if you could see it with your own eyes, reminiscent of Earth from space. But this resemblance is only surface deep. The blue color comes not from water, but from silicate particles suspended high in the atmosphere. These tiny fragments of glass scatter blue light, just as our own atmosphere does. The conditions here are far from tranquil. HD 18D9733b orbits so close to its star that temperatures soar to around 2,000 degrees Fahrenheit. The intense heat creates fierce weather systems, with winds screaming through the atmosphere at speeds exceeding 4,500 miles per hour. That's nearly 7 times the speed of sound. In these winds, those silicate particles don't simply float. Scientists believe they condense and fall as rain, but not the way rain falls on Earth. The extreme winds blow sideways, creating horizontal sheets of glass shards moving at supersonic speeds. It's a world where the very sky cuts like razors through perpetual azure storms. Yet even here, in conditions so hostile, we learn something profound about atmospheric dynamics and the surprising ways familiar materials can behave under extreme conditions. Move with me now to a planet caught in a gravitational dance with death. WASP-12b orbits its star so closely that it completes a full year in just one Earth day. This proximity creates a relationship that can only end one way. The star's gravity pulls at the planet with immense force, stretching it into an elongated egg-like shape. Material from the planet's atmosphere is constantly being stripped away, flowing toward the star in a stellar wind. The planet is quite literally being devoured, losing mass with each orbit. Scientists estimate that WASP-12b has perhaps 10 million years remaining before it's completely consumed, a short lifetime in cosmic terms. The planet is locked in tidal synchronization, meaning the same face always points toward its star, roasting at temperatures exceeding 4,000 degrees Fahrenheit. On the day side, the atmosphere may contain clouds of vaporized metals. The night side, forever facing away from the star, remains cooler, but still searingly hot. There's a strange melancholy to this world, caught in an inescapable spiral, each moment bringing it closer to its end. It reminds us that planetary systems are not static, frozen tableaus, but dynamic environments where worlds can be born, evolve, and eventually fade away. Many of the extreme worlds we're visiting share a common trait: tidal locking. This phenomenon occurs when a planet orbits very close to its star. Over time, gravitational forces synchronize the planet's rotation with its orbit, so one hemisphere perpetually faces the star while the other remains in eternal darkness. Think of our own moon, which is tidally locked to Earth. We always see the same face because the moon's rotation period matches its orbital period perfectly. For planets, this creates worlds of permanent day and endless night, with dramatic temperature differences between the two sides. Powerful winds rush from the scorching day side toward the frozen night side, trying endlessly to balance the temperature extremes. It's one of the many ways gravity shapes not just orbits, but the very conditions on planetary surfaces and in their atmospheres. Perhaps no exoplanet captures the imagination quite like WASP-76b, a world where the sky itself seems to bleed metal. This gas giant orbits a star in the constellation Pisces, roughly 640 light-years from Earth. The day side reaches temperatures around 4,500 degrees Fahrenheit, hot enough to vaporize iron. Strong winds carry this iron vapor across the planet toward the cooler night side. As the vapor crosses into the twilight zone between day and night, temperatures drop just enough for the iron to condense. And then it falls. Droplets of liquid iron cooling as they descend through the atmosphere, creating what scientists have dubbed iron rain. Imagine standing on the boundary between day and night on this world, watching a perpetual storm of metallic rain falling from rust-colored clouds. The air shimmers with heat. The horizon glows with the light of a nearby sun. And from above, iron falls like water, drop by luminous drop. It's a scene that seems pulled from science fiction, yet it exists, real and measurable, spinning through space as you rest here tonight. Not all extreme planets orbit in tidy circles. HD 606b follows a path so stretched, so elongated, that it experiences temperature swings unlike anywhere else we've found. At its farthest point from its star, HD 606b orbits at a comfortable distance. Temperatures hover around a balmy 800 degrees Fahrenheit, scorching by our standards, but relatively cool for a hot Jupiter. But then comes the plunge. Every 111 days, the planet's orbit brings it careening toward its star in a close approach that sends temperatures skyrocketing to over 2,000 degrees Fahrenheit in just 6 hours. That's a temperature increase of more than 200 degrees per hour. These thermal shocks create weather systems of unimaginable intensity. Massive storms erupt across the planet as the atmosphere rapidly expands. Winds accelerate to supersonic speeds. The entire planet transforms in the span of hours, then slowly settles as it swings back out into the cooler reaches of its orbit. It's a world of violent extremes, a reminder that orbital mechanics can create conditions just as hostile as proximity to a star. Here's a puzzle that seems to defy physics. A planet covered in ice, burning at temperatures of over 800 degrees Fahrenheit. Gliese 436b, orbiting a red dwarf star about 30 light-years away, shouldn't exist according to our everyday understanding of matter. At those temperatures, ice should vaporize instantly. Yet observations suggest this Neptune-sized world possesses a layer of water ice. The answer lies in pressure. Gliese 436b has such immense gravity that water molecules are compressed into exotic forms of ice that can remain solid even at extreme temperatures. This isn't the ice you'd find in your freezer, but rather ice variants with names like Ice C7 or Ice X, crystalline structures that can only exist under extraordinary pressure. It's water, frozen solid yet hot enough to boil. A contradiction made real by the extreme conditions found on worlds very different from our own. This planet teaches us that our intuitions about how matter behaves, formed on Earth at Earth pressures and temperatures, don't always apply in the wider universe. Imagine a world so diffuse, so low in density, that it almost seems to float like a soap bubble in space. WASP 127b is one of the least dense exoplanets ever discovered, earning it the nickname of a puffy planet. Despite being larger than Jupiter, WASP 127b has only a fraction of Jupiter's mass. Its atmosphere is stretched and tenuous, extending far into space. But don't let the puffy description fool you into thinking this is a gentle world. Winds race through the atmosphere at astonishing speeds, constantly reshaping the layers of gas. The James Webb Space Telescope has detected water vapor, carbon dioxide, and hints of clouds in this extended atmosphere. The planet is tidally locked, with permanent day and night sides driving continuous circulation patterns. These winds, moving at thousands of miles per hour, transport heat and materials around the planet in endless turbulent loops. It's a world that shows us planets can be far less dense than we ever imagined, their atmospheres puffed up by heat into enormous, storm-tossed spheres. Our journey brings us finally to Kelt 9b, a planet so hot it stretches our understanding of what a planet can be. Orbiting a star much hotter and brighter than our Sun, Kelt 9b experiences day-side temperatures around 7,800 degrees Fahrenheit. That's hotter than many small stars. It's hot enough that molecules in the atmosphere are ripped apart into their constituent atoms. On the day side, there are likely no molecules at all, just a scorching plasma of atomic gas. Even atoms of heavy metals are present in gaseous form. The planet is losing mass rapidly, evaporating into space under the intense radiation from its star. Scientists believe Kelty 9b may have once been significantly larger, slowly boiling away over millions of years. What remains is a world in the process of being destroyed by heat, a testament to how close a planet can orbit before the very concept of planet begins to break down. These worlds we visited tonight, each impossibly distant, each utterly hostile to life as we know it, represent just a tiny fraction of the exoplanets discovered so far. And those discoveries represent only a small sample of what must be countless trillions of planets in our galaxy alone. Sleep well, knowing the cosmos continues its ancient dance, and tomorrow we'll still be here, curious and watching, ready to discover what comes next.